Welcome, fellow cosmic wanderers, to the most extraordinary story ever told, the complete biography of our universe itself. Tonight, we're embarking on a journey that spans not just billions, but trillions upon trillions of years, from the very first moment of existence to the ultimate fate that awaits all of creation. As we settle in for this cosmic voyage, I'm curious, where are you joining us from tonight? Are you gazing up at city lights, or perhaps under a canopy of stars? And what time is it in your corner of the world as we begin this timeless journey together? Let your mind drift as we travel through the vastest story imaginable, where every chapter unfolds across unimaginable scales of time and space. Close your eyes and allow yourself to become a passenger on this ultimate voyage through the cosmos. Chapter 1. The first second genesis of everything. Time, 0 to 1 second after the Big Bang. In the beginning, there was nothing. No space, no time, no matter, no energy. Nothing that we could recognize as existence. And then, in an instant so brief it defies human comprehension, everything began. Picture, if you can, the moment at exactly 0 seconds. This isn't merely an explosion in space. This is the creation of space itself, along with time, matter, and energy. The universe springs into existence from a point smaller than the smallest particle we know, a singularity of infinite density and temperature. Where are you listening from tonight? In whatever peaceful space you've chosen, imagine that every atom in your body, every molecule of air you breathe, was once compressed into that infinitesimal point of pure potential. At 10 to the power of negative 43 seconds, that's a decimal point followed by 42 zeros and then a 1, we reach the Planck time, the smallest meaningful unit of time in physics. Before this moment, our understanding of physics itself breaks down. We've entered the realm of quantum gravity, where the very fabric of space-time itself fluctuates and foams like the surface of a turbulent ocean viewed from impossibly close. The temperature at this moment reaches an incomprehensible 10 to the power of 32 Kelvin. To put this in perspective, the core of our sun burns at about 15 million Kelvin. The early universe was billions upon billions of times hotter than the heart of our nearest star. As the universe expands, and remember, this expansion isn't an explosion moving through space, but the creation and stretching of space itself, the temperature begins to drop. At 10 to the power of negative 35 seconds, something remarkable happens. The universe undergoes what cosmologists call cosmic inflation, a period of exponential expansion that occurs faster than the speed of light. During inflation, the universe grows by a factor of at least 10 to the power of 26 in less than 10 to the power of negative 32 seconds. A region smaller than a proton suddenly becomes larger than a grapefruit. This might seem to violate Einstein's speed limit. Nothing can travel faster than light, but space itself is expanding, carrying matter along with it. The speed limit applies to motion through space, not the expansion of space itself. What time is it where you are as we witness this cosmic dawn? Whether it's evening, midnight, or the quiet hours before sunrise, know that we're exploring the ultimate beginning, when time itself was born. The inflation period ends as suddenly as it began, and the universe settles into a more conventional expansion. But the damage, so to speak, is done. What was once a tiny, causally connected region has been stretched to enormous size, which explains why the universe appears so uniform in temperature and structure across vast distances that light hasn't had time to traverse. As we approach the end of the first second, the temperature has dropped to about 10 billion Kelvin, still incredibly hot but cool enough for the first stable particles to form. Quarks, the building blocks of protons and neutrons, begin to bind together in a process called nucleosynthesis. The universe at this moment is a seething plasma of fundamental particles. Quarks combining into protons and neutrons, electrons dancing through the cosmic soup, and photons, particles of light, bouncing endlessly between charged particles in an opaque cosmic fog. By the end of the first second, we have the basic ingredients for everything that will follow: protons, neutrons, and electrons. The universe has grown from infinitesimal to approximately light seconds across, and its temperature has dropped to where nuclear physics, rather than exotic particle physics, governs the cosmic dance. Chapter 2. The first 3 minutes nuclear forging. Time: 1 second to 20 minutes after the Big Bang. As our cosmic story continues beyond that first crucial second, we enter what Nobel laureate Steven Weinberg famously called the first 3 minutes. A period when the universe became a vast nuclear reactor, forging the first atomic nuclei in the fires of creation itself. The temperature has now dropped to about 1 billion Kelvin, still unimaginably hot, but cool enough for nuclear fusion to begin. This is the moment when the universe starts cooking up the elements that will one day form stars, planets, and even the bodies of creatures who will look back and contemplate this very moment. I wonder, as you listen to this cosmic tale, are you in a quiet bedroom, perhaps watching the gentle glow of a night light? Or maybe you're outdoors, under the vastness of the night sky? Wherever you are, the hydrogen atoms in the water in your body are about to be born in our story. During these first few minutes, the universe is still far too hot for atoms to form. Instead, we have a plasma soup of free protons, hydrogen nuclei, neutrons, and electrons, all moving at tremendous speeds. The temperature is just right for nuclear fusion. The same process that powers our sun, but occurring throughout the entire universe. Free neutrons, which are unstable and normally decay in about 15 minutes, begin fusing with protons to form deuterium, heavy hydrogen with 1 proton and 1 neutron. This is a delicate dance of cosmic timing. If the universe had expanded too quickly, it would have cooled too fast for fusion to occur. If it had expanded too slowly, the temperature would have remained so high that any formed nuclei would have been immediately destroyed. As the minutes tick by, deuterium nuclei begin capturing additional protons and neutrons, building up to helium-3 and helium-4. A small amount of lithium-7 also forms. But the universe is expanding and cooling so rapidly that this cosmic nuclear reactor can only operate for a brief window. By about 20 minutes after the Big Bang, the temperature has dropped below 100 million Kelvin. Still incredibly hot by everyday standards, but too cool for nuclear fusion to continue. The cosmic nuclear furnace shuts down, having created what we call the primordial abundance of light elements. About 75% hydrogen, 25% helium, and trace amounts of deuterium and lithium. This primordial ratio of hydrogen to helium is one of the most powerful pieces of evidence for the Big Bang theory. When we look at the oldest stars in our galaxy today, we find exactly this ratio, unchanged since those first minutes when the universe forged its first atomic nuclei. What's remarkable is that despite the universe containing billions upon billions of stars, all the stellar fusion that has occurred over the past 13.8 billion years has barely changed these primordial ratios. Stars have created heavier elements, the carbon in our bodies, the oxygen we breathe, the iron in our blood, but hydrogen and helium remain dominant, testament to those first crucial minutes of cosmic nucleosynthesis. As we reach the 20-minute mark, the universe has grown to roughly the size of our current solar system, with a temperature of about 100 million Kelvin. But we're still in a plasma state. Electrons are moving too rapidly to be captured by atomic nuclei, and the universe remains opaque to light, a cosmic fog through which photons cannot travel freely. This fog will persist for hundreds of thousands of years, but the crucial nuclear work is done. The universe now contains all the hydrogen and helium it will ever produce through Big Bang nucleosynthesis. Everything heavier will have to wait for the first stars to form, beginning the next great chapter in cosmic evolution. Chapter 3. The Dark Ages begin. Matter takes control. Time: 20 minutes to 380,000 years after the Big Bang. As our journey through cosmic time continues, we enter what astronomers poetically call the Dark Ages, Not because this period lacks importance, but because it's a time when the universe produces no light that can travel freely through space. We're entering the longest night in cosmic history, a period that will last hundreds of thousands of years. By now, about an hour after the Big Bang, the cosmic nuclear reactor has shut down, leaving behind a universe filled with roughly 75% hydrogen nuclei, 25% helium nuclei, and a tiny sprinkling of deuterium and lithium. But these are still just bare atomic nuclei, racing through space with their electron companions in a state of matter called plasma. Where are you joining our cosmic voyage tonight? Perhaps it's late evening where you are, making it perfect timing to explore this era of cosmic darkness. What better time to contemplate the dark ages of the universe than during the quiet hours of your own world's night? The universe at this time is completely opaque. Imagine the thickest fog you've ever experienced, so dense you can't see your hand in front of your face. The early universe is like this, but with light instead of vision. Photons, particles of light, are constantly colliding with free electrons, scattering in random directions. Light cannot travel in straight lines for any significant distance. The universe is dark not because there's no light, but because light cannot travel freely. As centuries pass, then millennia, the universe continues its relentless expansion. With expansion comes cooling, and with cooling comes a gradual shift in the cosmic balance of power. During the first few thousand years, radiation, photons, and other massless particles dominated the universe's energy budget. But as space expands, radiation becomes diluted more quickly than matter. This is a subtle but crucial point in cosmic evolution. Radiation pressure decreases as the fourth power of the universe's size, while matter density decreases only as the cube. Eventually, around 50,000 years after the Big Bang, matter begins to dominate over radiation. This transition marks the beginning of the matter-dominated era, which will continue for billions of years. During this long, dark period, something remarkable happens on the smallest scales. Although the universe appears smooth to us, there were tiny quantum fluctuations present from the very beginning. Microscopic variations in density that were stretched to cosmic proportions during the inflation period we discussed earlier. These density variations, initially just 1 part in 100,000, begin to grow under their own gravitational influence. Regions that are slightly denser than average start to attract more matter, becoming denser still. Meanwhile, regions that are slightly less dense become emptier as their matter migrates toward the denser regions. It's like a cosmic game of rich get richer, but instead of wealth, we're talking about matter density. Over hundreds of thousands of years, these tiny variations grow into the seeds of cosmic structure, the future locations of galaxy clusters, galaxies, and stellar nurseries. The universe during this time is cooling steadily. By about 100,000 years after the Big Bang, the temperature has dropped to about 1,000 Kelvin, roughly the temperature of glowing lava. Still far too hot for atoms to form, but we're getting closer to that crucial threshold. Dark matter, which doesn't interact electromagnetically and therefore doesn't contribute to the cosmic fog, begins to clump together more efficiently than ordinary matter. These dark matter halos grow and merge, creating the invisible scaffolding upon which future galaxies will form. As we approach 380,000 years after the Big Bang, the temperature has dropped to about 3,000 Kelvin, roughly the temperature of a tungsten light bulb filament. This is the crucial threshold temperature. Below this point, electrons finally move slowly enough to be captured by atomic nuclei, forming the first neutral atoms in cosmic history. The stage is set for one of the most important transitions in the universe's history: recombination, the moment when the cosmic fog will lift and the universe will become transparent to light for the first time. We stand on the threshold of cosmic dawn, when the dark ages will end and the universe will release its first free light that we can still detect today as the cosmic microwave background radiation. Chapter 4. Let There Be Light, the Cosmic Microwave Background. Time 380,000 years after the Big Bang. After nearly 400,000 years of cosmic darkness, we've arrived at one of the most pivotal moments in the universe's history. A moment astronomers call recombination, though it's really the first time atomic combination has occurred. This is the universe's equivalent of sunrise after the longest night imaginable. As you listen to this cosmic story unfold, I'm curious about your own moment in time. What's the hour where you are? Are you perhaps settling in for sleep as we explore the moment when the universe first woke up? There's something beautifully symmetrical about contemplating cosmic dawn during your own transition toward rest. The universe has now cooled to about 3000 Kelvin, still hot enough to melt copper, but finally cool enough for something magical to happen. Electrons, which have been racing freely through space for hundreds of thousands of years, finally slow down enough to be captured by atomic nuclei. Picture this moment. Throughout the entire universe, almost simultaneously, electrons begin settling into orbits around protons and helium nuclei. For the first time in cosmic history, neutral atoms form on a universal scale. The universe suddenly becomes transparent to light. This transition doesn't happen gradually, it occurs relatively quickly, over just a few thousand years. One moment the universe is opaque, the next it's crystal clear. It's as if a cosmic fog that had shrouded everything suddenly lifts, revealing the universe in all its primordial glory. The light that had been trapped, constantly scattering off free electrons, is suddenly free to travel in straight lines across the cosmos. This is the cosmic microwave background radiation, the afterglow of creation itself. Every cubic centimeter of space is filled with these ancient photons, the oldest light in the universe, carrying with them a snapshot of what the cosmos looked like when it was less than 400,000 years old. What's truly remarkable is that we can still detect this light today. It has been traveling through space for over 13 billion years, growing steadily redder and cooler as the universe expands. When it was first released, this light glowed at visible wavelengths, like the warm red glow of a heating element. Today, stretched by cosmic expansion, it appears as microwave radiation with a temperature of just 2.7 Kelvin, barely warmer than absolute zero. In 1965, two Bell Labs engineers, Arno Penzias and Robert Wilson, accidentally discovered this cosmic microwave background while trying to eliminate a persistent noise in their radio antenna. They had stumbled upon the echo of creation itself, earning them the Nobel Prize and providing powerful evidence for the Big Bang theory. Modern satellites like COBE, WMAP, and Planck have mapped this ancient light with extraordinary precision, revealing tiny temperature variations, the fossil imprints of those quantum fluctuations from the first fraction of a second after the Big Bang. These variations, just millionths of a degree in temperature difference, represent the seeds of all cosmic structure. The slightly warmer regions in the cosmic microwave background correspond to areas that were slightly denser when recombination occurred. These would become the locations of future galaxy clusters. The slightly cooler regions were less dense and would become the vast cosmic voids that separate clusters of galaxies. As recombination completes, the universe enters what we might call its childhood, transparent, filled with neutral hydrogen and helium atoms, but still without stars or galaxies. The temperature continues to drop as expansion continues. By now, the universe is about 84 million light-years across and cooling rapidly. This moment, 380,000 years after the Big Bang, represents the oldest direct observation we can make of the universe. It's our cosmic horizon. When we look at the cosmic microwave background, we're seeing the universe as it was when it first became transparent, frozen in time like an ancient photograph. The atoms formed during recombination are simple. Mostly hydrogen, 1 proton, 1 electron, and helium, 2 protons, 2 neutrons, 2 electrons. There are no heavy elements yet, No carbon, no oxygen, no silicon, no iron. The universe is chemically pristine, composed almost entirely of the lightest elements created during Big Bang nucleosynthesis. As we leave this crucial epoch behind, the universe is about to enter another dark period. Not because it's opaque, but because there are no sources of light yet. No stars, no galaxies, no quasars. Just vast expanses of neutral gas slowly clumping together under gravity's patient influence, setting the stage for the next great act in cosmic evolution, the formation of the first stars. Chapter 5, The Second Dark Ages, Building the Cosmic Web. Time 380,000 to 150 million years after the Big Bang. Having witnessed the cosmic dawn when the universe first became transparent, we now enter what might seem like a step backward, the second period of cosmic darkness. But this darkness is different from the first. The universe is now transparent, but there simply aren't any light sources yet. It's like having perfect vision in a world where no one has yet invented the light bulb. As we drift through this cosmic night, I wonder about your own surroundings. Are you in a cozy, dimly lit room? Perhaps with just the soft glow of a device screen? It's fitting to explore this dark chapter of cosmic history in the gentle darkness of your own evening. The universe at this time consists almost entirely of neutral hydrogen and helium gas, slowly cooling as space continues to expand. The temperature has dropped from 3000 Kelvin at recombination to just a few dozen Kelvin, colder than the coldest winter night on Earth, but still above absolute zero. This might seem like a boring period in cosmic history, but beneath the apparent emptiness, momentous changes are occurring. Those tiny density variations we mapped in the cosmic microwave background, differences of just millionths of a degree, are now growing under their own gravitational influence. Imagine the universe as a vast, nearly smooth sheet of fabric with the tiniest wrinkles. Over millions of years, these wrinkles deepen. Gravity pulls matter from the less dense regions into the slightly denser ones. What started as almost imperceptible variations gradually become more pronounced. Dark matter, which makes up about 27% of the universe but doesn't interact with light, leads this cosmic construction project. Unhindered by electromagnetic forces, dark matter particles can clump together more efficiently than ordinary matter. They form an invisible scaffolding, creating the framework upon which future galaxies will assemble. Computer simulations of this period reveal a universe that's beginning to look like a cosmic web. Vast filaments of dark matter stretch across space, with massive nodes where these filaments intersect. Between the filaments lie enormous voids, regions that will remain largely empty for billions of years to come. The ordinary matter, hydrogen and helium gas, follows the gravitational lead of dark matter, flowing along these invisible highways like water following the channels carved by rivers. Gas accumulates in the deepest gravitational wells, where dark matter is most concentrated. What time is it in your world as we explore this era of cosmic construction? Whether it's late evening or the deep hours of night, we're witnessing the universe slowly assembling the architecture that will define its appearance for billions of years to come. As millions of years pass, the largest dark matter halos grow more massive, eventually reaching the point where they can trap and hold onto gas. The first protogalactic structures begin to form, not yet galaxies as we know them, but the precursors that will eventually host the first stars. The universe during this time is remarkably cold and quiet. The cosmic microwave background provides the only source of energy, and even that is steadily cooling as the universe expands. Gas temperatures drop to just 10 to 20 Kelvin, just barely above absolute zero. But gravity is patient and relentless. Slowly, inexorably, matter continues to flow toward the deepest gravitational wells. As gas accumulates in these regions, it begins to heat up slightly due to gravitational compression. The first protogalactic halos reach masses equivalent to millions of solar masses. By about 100 million years after the Big Bang, the largest dark matter halos have grown massive enough and dense enough to begin trapping significant amounts of gas. The stage is being set for one of the most important events in cosmic history, the formation of the first stars. These early dark matter halos are much smaller than the galaxies we see today, perhaps 1/100th the mass of our Milky Way. But they represent the first stepping stones in the universe's journey from smooth simplicity to the rich complexity we observe today. The cosmic web structure that emerges during this period will persist throughout the universe's history. Even today, 13.8 billion years later, galaxies are arranged along filaments separated by vast voids, following the blueprint laid down during these early dark ages. As we approach 150 million years after the Big Bang, conditions in the deepest gravitational wells are finally becoming extreme enough for something extraordinary to happen. Gas densities are reaching critical thresholds, and the first molecular hydrogen, H2, is beginning to form through chemical reactions in the cosmic gas. Molecular hydrogen is crucial because it's an efficient coolant, allowing gas clouds to collapse more effectively under their own gravity. We're approaching the moment when the universe's second dark age will end not with transparency, as the first did, but with the ignition of the first stars, cosmic beacons that will burn away the darkness and begin the universe's transformation into the light-filled cosmos we know today. Chapter 6. The First Stars, Cosmic Pioneers. Time 150 to 300 million years after the Big Bang. After more than 100 million years of darkness, the universe is about to experience its second great awakening. Deep within the most massive dark matter halos, gas clouds are finally dense enough and cool enough to collapse under their own gravity. We stand at the threshold of stellar dawn, when the first nuclear furnaces will ignite and end the cosmic dark ages forever. These first stars, astronomers call them population 3 stars, will be unlike any stars that exist today. They're forming from the primordial gas created during Big Bang nucleosynthesis, roughly 75% hydrogen, 25% helium, and virtually nothing else. No carbon, no oxygen, no silicon, no iron, none of the heavier elements that help modern stars form efficiently. As you listen to this tale of cosmic awakening, what time marks your own evening? Are you perhaps in those quiet hours when your own world settles into darkness, making this the perfect time to explore the moment when the universe first lit up with starlight? The absence of heavy elements makes star formation much more difficult in the early universe. In modern molecular clouds, carbon and oxygen form compounds that help gas cool and collapse. But the primordial universe lacks these cooling agents, so only the most massive gas clouds can overcome their internal pressure and begin to collapse. Picture the scene. A dark matter halo perhaps 1,000,000 times the mass of our Sun, filled with primordial gas slowly flowing inward under gravity's influence. As the gas compresses, it heats up, but molecular hydrogen, the only available coolant, struggles to radiate away the thermal energy. Only the very center of the most massive clouds can achieve the extreme densities needed for star formation. When these first stellar cores finally ignite, they're monsters by today's standards. While typical stars today range from 1/10 to perhaps 100 times our Sun's mass, these population 3 pioneers likely weighed in at 100 to 1,000 solar masses, some possibly even larger. They burn blue-hot and incredibly bright, consuming their nuclear fuel at prodigious rates. The first star to ignite creates a bubble of intense radiation in the surrounding primordial gas. Its ultraviolet light begins ionizing hydrogen atoms, creating the first H2 region, a glowing nebula of hot, ionized gas surrounding the newborn star. For the first time since recombination, parts of the universe are once again ionized, but now by starlight rather than the ambient heat of the Big Bang. These stellar giants live fast and die young. While our Sun will burn for about 10 billion years, a population 3 star exhausts its nuclear fuel in just a few million years. But what spectacular lives they lead. Their surfaces burn at temperatures of 50,000 Kelvin or more, several times hotter than our sun, blazing with the luminosity of millions of modern stars. Inside their cores, nuclear fusion operates at an incredible pace. Starting with hydrogen burning, they quickly progress through helium burning, creating carbon and oxygen. As their cores heat up further, they synthesize neon, magnesium, silicon, and eventually iron, the first heavy elements the universe has ever known. When these stellar titans finally exhaust their fuel, they don't fade gently into white dwarfs like smaller stars will do billions of years later. Instead, they explode as supernovae so energetic they outshine entire galaxies. These explosions serve as the universe's first heavy element factories, scattering newly forged carbon, oxygen, silicon, and iron into the surrounding space. But the story gets even more dramatic. The most massive population 3 stars, those exceeding perhaps 260 solar masses, may have met an even more exotic fate. They might have collapsed directly into intermediate mass black holes, creating some of the first black holes in the universe and potentially seeding the supermassive black holes we find at galaxy centers today. The first generation of stars transforms the universe in multiple ways. Their intense ultraviolet radiation begins the process of reionization, gradually ionizing the neutral hydrogen throughout space. Their stellar winds and supernova explosions heat and enrich the surrounding gas with heavy elements. And their gravitational influence helps trigger the formation of additional stars in nearby gas clouds. By about 300 million years after the Big Bang, star formation is becoming more widespread. The first small galaxies, really just loose associations of stars and gas held together by dark matter, begin to take shape. These proto-galaxies are tiny compared to modern galaxies, containing perhaps millions rather than hundreds of billions of stars. What's remarkable is that we may soon be able to observe these first stars directly. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is designed to peer back to this era of cosmic history. The light from population 3 stars has been traveling through space for over 13 billion years, stretched by cosmic expansion from visible wavelengths into the infrared, exactly where JWST excels. As the first stellar generation comes to an end, the universe has been fundamentally transformed. No longer is it composed purely of hydrogen and helium. Scattered throughout the cosmos are the ashes of dead stars, carbon atoms that will one day form organic molecules, oxygen that will become part of water, iron that will flow through the veins of living creatures on distant worlds. The cosmic dark ages are ending. The universe has tasted starlight and will never again return to universal darkness. We're about to enter an era of increasing brightness and complexity, as successive generations of stars build upon the chemical legacy of their predecessors. Chapter 7. The Dawn of Galaxies, Islands in the Cosmic Dark. Time 300 million to 1 billion years after the Big Bang. As the first stars fade and explode, scattering their newly forged elements into space, the universe enters a period of rapid transformation. We're witnessing the birth of the first true galaxies, not the massive spiral and elliptical giants we see today, but their small, chaotic ancestors that will eventually merge and grow into the cosmic cities of stars we know. The universe at 300 million years after the Big Bang is a very different place than it was just 150 million years earlier. Scattered throughout space are pockets of star formation, each one hosted by a dark matter halo and fed by the continuous infall of gas from the cosmic web. These early star-forming regions are the building blocks of galaxies. As you continue this cosmic journey with me, I'm curious about your own peaceful moment. Are you settling deeper into relaxation as we explore how the universe was settling into its first stable structures? What hour marks your evening as we travel through cosmic time? Unlike the massive population 3 stars that came before, this new generation of stars, population 2, forms from gas that has been enriched with heavy elements by the death of their predecessors. Even tiny amounts of carbon and oxygen make star formation much more efficient, allowing smaller clouds to collapse and creating stars across a much wider range of masses. These early galaxies are remarkably active places. Star formation rates are often 10 to 100 times higher than what we observe in modern galaxies. The reason is simple. These young galaxies are still being fed by continuous streams of fresh gas flowing in along dark matter filaments. They're growing rapidly, both in mass and in the rate at which they convert gas into stars. The first galaxies are also much smaller than their modern descendants. A typical early galaxy might contain only a few million to a few hundred million stars, compared to the hundreds of billions of stars in galaxies like our Milky Way. But what they lack in size, they make up for in energy and activity. Imagine peering into one of these primordial galaxies. Brilliant blue stars blaze throughout small, irregular clusters of gas and dust. Massive stars live their brief, violent lives and explode as supernovae at rates perhaps 100 times higher than in today's galaxies. The interstellar medium, the gas between stars, is a chaotic soup of shock waves, stellar winds, and expanding supernova remnants. These frequent stellar explosions serve multiple purposes in galactic evolution. They heat the surrounding gas, sometimes blowing it entirely out of the galaxy in powerful galactic winds. They mix heavy elements throughout the galaxy, ensuring that each new generation of stars is more metal-rich than the last. And they trigger the formation of new stars by compressing nearby gas clouds. The supermassive black holes that will eventually reside at the centers of large galaxies are also beginning to form during this period. Some may have grown from the remnants of the most massive population 3 stars, while others might have formed through direct collapse of primordial gas clouds. These early black holes are still relatively small, thousands to millions of solar masses rather than the billions of solar masses they'll eventually achieve. As gas falls into these early black holes, it forms accretion disks that shine brilliantly as quasars, the most luminous objects in the universe. Early quasars can outshine their entire host galaxies, visible across billions of light-years of space. They serve as cosmic lighthouses, illuminating the early universe and providing crucial feedback that regulates star formation in their host galaxies. The process of cosmic reionization accelerates during this period. The combined ultraviolet radiation from millions of young stars and thousands of quasars gradually ionizes the neutral hydrogen that fills intergalactic space. This is a patchy process. Some regions become ionized early, while others remain neutral for hundreds of millions of years longer. By about 600 million years after the Big Bang, roughly half of the universe's hydrogen has been reionized. Galaxy formation becomes more difficult in highly ionized regions because the increased gas pressure makes it harder for small dark matter halos to retain their gas. This creates a feedback loop that regulates the formation of the smallest galaxies. What time is it in your world as we witness these first galactic communities forming? Whether it's evening or night where you are, we're exploring the universe's own transition from the simplicity of its youth to the growing complexity of its adolescence. The early galaxies don't exist in isolation. They're beginning to interact with each other. Gravitational encounters cause some galaxies to merge, creating larger, more massive systems. These mergers often trigger intense bursts of star formation as gas clouds collide and compress. They also help build up the central black holes, as the black holes from merging galaxies eventually spiral into each other. The cosmic web structure becomes more pronounced during this period. Galaxies form preferentially along dark matter filaments, creating the first large-scale structures. Protoclusters of galaxies begin to assemble where multiple filaments intersect, though these early clusters contain only dozens of galaxies rather than the thousands we see in rich clusters today. By 1 billion years after the Big Bang, the universe has been transformed from a dark, nearly empty expanse to a cosmos filled with billions of small, active galaxies. The era of reionization is nearing completion, with only the densest pockets of neutral gas remaining unionized. Star formation is at its peak activity level, converting primordial gas into stars at a rate the universe will never again match. The chemical evolution of the universe has progressed remarkably. While the first stars contained virtually no heavy elements, stars forming at this epoch might contain 1/100th to January 10th the heavy element abundance of our Sun. Enough to begin forming the first solid particles that will eventually grow into planets. We're approaching one of the most active and violent periods in cosmic history, the era when galaxy formation and black hole growth reach their peaks, when quasars blaze at maximum brightness, and when the large-scale structure of the universe begins to resemble the cosmic web we observe today. Chapter 8, The Quasar Era When Black Holes Ruled the Cosmos. Time 1 to 3 billion years after the Big Bang. We now enter one of the most spectacular periods in cosmic history, the age of quasars, when supermassive black holes at the centers of young galaxies blazed with the fury of 1 trillion suns. This is the universe at its most energetic and violent, a time when black holes grew rapidly and their incredible luminosity could be seen across billions of light-years of space. The universe is now 1 to 3 billion years old. Still quite young by cosmic standards, but old enough for the first generation of galaxies to have grown substantially through mergers and continuous gas accretion. These early galaxies are feeding their central black holes at prodigious rates, creating the most luminous objects the universe has ever known. As we explore this era of cosmic violence and beauty, I wonder about the tranquil moment you're experiencing. Are you perhaps in the quiet hours of your evening, finding peace as we journey through the universe's most turbulent epoch? What time marks your passage through this cosmic tale? Picture a typical quasar from this era. At its heart lies a supermassive black hole containing millions to billions of times the mass of our Sun. Surrounding this black hole is an accretion disk of superheated gas spiraling inward at nearly the speed of light. As this gas approaches the black hole's event horizon, gravitational forces heat it to temperatures of millions of degrees, causing it to shine brilliantly across the entire electromagnetic spectrum. The energy output is staggering. A single quasar can outshine its entire host galaxy, which itself contains hundreds of millions or billions of stars. The most luminous quasars generate more energy in 1 second than our Sun will produce in its entire 10 billion-year lifetime. This energy comes not from nuclear fusion, but from the gravitational potential energy of matter falling into the black hole, the most efficient energy conversion process known in physics. But quasars don't just shine, they actively reshape their surroundings. Powerful jets of charged particles, accelerated to nearly the speed of light, shoot out from the poles of the spinning black hole. These jets can extend for millions of light-years, far beyond the host galaxy itself, depositing enormous amounts of energy into the surrounding intergalactic medium. The radiation pressure from quasars is so intense that it can literally blow gas out of their host galaxies in powerful galactic winds. This creates a natural regulation mechanism. As a black hole grows more massive and luminous, it becomes increasingly effective at expelling the very gas that feeds it. Eventually, the quasar shuts down when it runs out of fuel, and the black hole enters a quiescent phase. This period represents the peak of cosmic star formation as well. The universe is converting gas into stars at the highest rate in its history, roughly 10 times more actively than today. The combination of abundant gas supplies, frequent galaxy mergers, and the triggering effects of quasar activity creates ideal conditions for rapid stellar birth. The early galaxies hosting these quasars are quite different from the large, well-organized spiral and elliptical galaxies we see today. They're smaller, more irregular, and often show signs of recent mergers. Many appear to be in the process of assembling from smaller building blocks, with streams of gas and clusters of stars arranged in chaotic, asymmetric patterns. During this era, the most massive galaxies are forming through the merger of smaller systems. When two gas-rich galaxies collide, their central black holes eventually spiral toward each other, creating one of the most violent events in the universe: a supermassive black hole merger. The gravitational waves from such events would ripple through spacetime itself, though we lack the technology to detect these ancient waves. Galaxy clusters are also beginning to mature during this period. The largest structures in the universe start as modest collections of a few dozen galaxies, but gravitational attraction causes them to grow rapidly. As galaxies fall into these forming clusters, their motion through the increasingly dense intracluster medium begins to strip away their outer gas, a process that will eventually transform gas-rich spiral galaxies into gas-poor elliptical systems. What's your local time as we witness this cosmic peak of activity? Whether you're in the peaceful evening hours or the deep quiet of night, we're exploring when the universe was at its most energetic and transformative. The intergalactic medium, the gas that fills the space between galaxies, is also undergoing dramatic changes. The intense ultraviolet radiation from quasars and young stars completes the reionization process that began with the first stars. By about 1 billion years after the Big Bang, virtually all hydrogen in the universe has been ionized, ending the last remnants of the cosmic dark ages. This reionized gas doesn't remain smooth and uniform. The radiation from quasars and star-forming galaxies heats it unevenly, creating a complex temperature structure. Some regions remain relatively cool and dense, while others are heated to millions of degrees and become highly rarefied. This temperature structure will persist for billions of years, influencing how gas flows between galaxies and where new stars can form. The heavy element content of the universe increases dramatically during this period. Each generation of stars adds more carbon, oxygen, silicon, and iron to the cosmic inventory. By 2 to 3 billion years after the Big Bang, some regions of space contain enough heavy elements to begin forming the first solid particles, dust grains that will eventually coalesce into planets. The first planetary systems are likely forming during this era, though they would be quite different from our solar system. Composed primarily of hydrogen, helium, and the limited heavy elements available, these early planets would be mostly gaseous or icy worlds. True rocky, terrestrial planets capable of supporting life, as we know, it will have to wait for more heavy elements to be produced by stellar nucleosynthesis. As we approach 3 billion years after the Big Bang, the quasar era begins to wind down. The most massive black holes have grown so large that they've consumed or expelled most of the available gas in their vicinity. Star formation rates, while still high, begin to decline from their peak levels. The universe is transitioning from its wild, chaotic youth toward a more mature and organized middle age. The cosmic web structure is now clearly defined, with galaxies arranged along filaments separated by vast voids. The largest galaxy clusters contain hundreds of members and span millions of light-years. The basic architecture of the modern universe is taking shape, though continued evolution will refine and elaborate on these structures for billions of years to come. Chapter 9. The Peak of Creation, Cosmic High Noon. Time 3 to 7 billion years after the Big Bang. As our cosmic journey continues, we enter what astronomers call cosmic high noon, the period when star formation reaches its absolute peak and the universe transforms gas into stars more rapidly than at any other time in cosmic history. This is the universe in its creative prime, building the stellar populations that will define galactic structure for billions of years to come. By 3 billion years after the Big Bang, the initial chaos of the quasar era is beginning to settle into more organized patterns. Galaxies have grown larger through mergers and accretion, Their central black holes have reached impressive masses, and the cosmic web of dark matter has become a well-defined highway system along which gas and galaxies flow. The star formation rate across the universe during this period is truly staggering. If we could somehow count all the stars being born every second throughout the observable universe, we would find roughly 100 times more stellar births than occur today. This isn't because individual galaxies are necessarily more active than modern ones, but because there are many more actively star-forming galaxies, and they have access to vast reservoirs of fresh, unused gas. As you drift through this cosmic tale, what moment in your own day or night marks this journey? Are you finding peace in the evening hours as we explore the universe's most creative period? The timing seems fitting, exploring cosmic high noon during your own transition toward rest. The galaxies of this era are remarkably diverse. Some have grown through mergers into early elliptical systems, their star formation largely complete and their stellar populations beginning to age. Others remain gas-rich spirals, continuously forming new stars along elegant spiral arms. Still others are caught in the act of merging, creating spectacular starbursts as their gas supplies collide and compress. These starburst galaxies represent some of the most extreme star-forming environments in cosmic history. During a major galactic merger, two gas-rich spirals can convert their entire gas supplies into stars within just a few 100 million years, a cosmic eye blink. The resulting systems blaze with the light of billions of newly formed stars, often obscured by the dust produced by their own stellar activity. The heavy element content of the universe continues to climb during this period. Each generation of massive stars lives, dies, and enriches the interstellar medium with carbon, oxygen, silicon, iron, and dozens of other elements. By cosmic high noon, typical star-forming regions contain perhaps half the heavy element abundance we see in our solar neighborhood today, enough to begin forming substantial populations of rocky planets. This is likely when the first truly Earth-like worlds begin to appear. With sufficient rocky material available and increasingly sophisticated planetary formation processes, solar systems start to include not just gas giants and ice worlds, but solid, terrestrial planets with the potential to develop atmospheres, oceans, and possibly even life. The supermassive black holes at galaxy centers have also matured considerably. Most have grown to masses of millions or billions of solar masses, and many have entered relatively quiet phases as they've consumed or expelled the gas in their immediate vicinity. The era of brilliant quasars is waning, though active galactic nuclei continue to play important roles in regulating star formation and heating the intergalactic medium. Galaxy clusters are becoming impressive structures during this period. The largest contain hundreds of galaxies bound together by gravity, with total masses exceeding 10 to the power of 14 solar masses, as much as 100 trillion suns. The space between cluster galaxies is filled with hot, X-ray emitting gas at temperatures of tens of millions of degrees, heated by the gravitational energy released as the cluster assembled. Within these clusters, we begin to see the environmental effects that will shape galaxy evolution for the remainder of cosmic history. Galaxies moving through the hot intracluster medium experience ram pressure stripping. The cluster gas literally blows away their outer gas layers like wind stripping leaves from a tree. This process gradually transforms gas-rich spiral galaxies into gas-poor elliptical systems. The cosmic web structure reaches full maturity during this epoch. Dark matter filaments span hundreds of millions of light-years, channeling gas flow between galaxy clusters and isolated field galaxies. The largest voids, regions nearly empty of galaxies, have grown to enormous sizes, some spanning over 100 million light-years across. What time is it in your world as we explore this peak of cosmic creativity? Whether it's evening, night, or the quiet hours before dawn, we're witnessing the universe at its most productive, when the basic structure of the modern cosmos crystallizes into the patterns we observe today. The interplay between star formation, stellar death, and gas recycling reaches a sophisticated equilibrium during cosmic high noon. Massive stars form, live their brief lives, and explode as supernovae, heating and enriching the surrounding gas. This heated gas may be expelled from smaller galaxies entirely, while in larger systems it cools and condenses to form new generations of stars. The cycle repeats, gradually building up the heavy element content and regulating the overall rate of star formation. By about 7 billion years after the Big Bang, signs of cosmic aging begin to appear. The star formation rate, while still high, starts its long decline toward modern levels. The universe has consumed much of its initial gas supply, converting it into stars or heating it to such high temperatures that it can no longer easily cool and collapse. The era of peak creativity is coming to an end, and the universe is about to transition into its mature phase. This transition doesn't happen suddenly. It unfolds over billions of years as gas supplies are gradually exhausted and stellar populations age. But the fundamental character of the universe is shifting from rapid growth and high activity toward the more sedate, slowly evolving cosmos we inhabit today. As cosmic high noon draws to a close, the universe has established most of the structures and patterns that will define its appearance for the remainder of its history. Massive elliptical galaxies anchor rich clusters. Spiral galaxies continue forming stars at moderate rates along their elegant arms, and the cosmic web provides the framework along which all evolution will proceed. Chapter 10: The Rise of Structure Building the Modern Universe. Time 7 to 10 billion years after the Big Bang. As the universe passes its 7th billion birthday, we witness a gradual but profound transformation. The wild, chaotic activity of cosmic youth gives way to the more organized, slowly evolving patterns of galactic maturity. Star formation rates begin their long decline from the peaks of cosmic high noon, and the large-scale structure of the universe approaches its modern form. This is the era when many of the galaxy types we recognize today crystallize into their familiar forms. The great spiral galaxies develop their elegant, symmetric arms wound around central bulges. Massive elliptical galaxies, their star formation largely complete, begin their long evolution toward the red, aged stellar populations we observe in local clusters. Irregular and dwarf galaxies continue their more chaotic evolution, often influenced by gravitational interactions with their larger neighbors. The Milky Way galaxy itself is taking shape during this period. Like other large spirals, it's assembled through the merger of smaller building blocks, dwarf galaxies and star clusters that gradually settle into the rotating disk structure we know today. Our galaxy's central supermassive black hole, Sagittarius A*, grows through accretion and possibly mergers with black holes from infalling satellite galaxies. As you continue this cosmic journey, I'm curious about your own moment of tranquility. What hour marks your evening as we explore this era of cosmic organization? Are you finding peace in the gradual rhythm of this story, much like the universe itself was settling into more predictable patterns? The chemical evolution of the universe continues during this period, though at a more measured pace than during the frenzied star formation of earlier epochs. Each generation of stars adds to the cosmic inventory of heavy elements, gradually enriching the interstellar medium to levels that begin to approach modern values. By 8 to 9 billion years after the Big Bang, star-forming regions contain roughly the same abundance of heavy elements as our Sun, which formed about 4.6 billion years ago. This chemical enrichment has profound implications for planetary formation. The first generation of truly Earth-like worlds, rocky planets with substantial atmospheres and the potential for liquid water oceans, likely forms during this epoch. These worlds represent the earliest opportunities for complex chemistry and possibly life as we know it. The galaxy cluster hierarchy continues to develop during this period. Small groups merge to form larger clusters, which themselves combine to form superclusters, the largest gravitationally bound structures in the universe. the local supercluster which contains our Milky Way, the Andromeda Galaxy, and thousands of other galaxies, likely assembled during this era. Within galaxy clusters, the hot intracluster medium reaches temperatures of 50 to 100 million Kelvin, hot enough to emit copious X-rays and strip gas from infalling galaxies. This process, combined with gravitational interactions between cluster members, transforms the galaxy population. Gas-rich spiral galaxies gradually become gas-poor ellipticals through a combination of ram pressure stripping, tidal interactions, and the consumption of their gas supplies through star formation. The cosmic web structure reaches full maturity during this period. Computer simulations show that by about 8 billion years after the Big Bang, the large-scale distribution of matter closely resembles what we observe in the local universe today. Dark matter filaments connect galaxy clusters across hundreds of millions of light-years, while vast voids, regions nearly empty of galaxies, occupy most of the universe's volume. Star formation, while declining from its peak rates, continues at substantial levels throughout this period. However, the character of star formation changes. Early in cosmic history, star formation was often triggered by dramatic events like galaxy mergers and interactions. During this more mature phase, star formation becomes increasingly dominated by the steady, secular processes that operate within individual galaxies, the gradual accumulation of gas in spiral arms, the compression of molecular clouds by stellar winds and supernovae, and the recycling of material through stellar death and birth cycles. What time is it where you are as we witness this cosmic coming of age? Whether you're in the peaceful evening hours or the deeper quiet of night, we're exploring when the universe developed the patterns and structures that would persist for billions of years into the future. The supermassive black holes at galaxy centers continue to grow during this period, though generally at more modest rates than during the quasar era. Most have entered relatively quiet phases, accreting gas at low rates and producing much less dramatic activity than their younger, more active counterparts. However, they continue to play crucial roles in regulating star formation within their host galaxies through a process astronomers call feedback. When gas does fall toward a central black hole, the resulting energy output, even at relatively low levels, can heat the surrounding medium enough to prevent further cooling and star formation. This creates a self-regulating system where black hole growth and stellar activity balance each other, explaining why we observe such tight correlations between black hole masses and the properties of their host galaxies. The first complex organic molecules likely form in substantial quantities during this epoch. With sufficient heavy elements available and increasingly sophisticated planetary systems developing around sun-like stars, the chemical foundations for life as we know it become widespread throughout the universe. Carbon-based chemistry begins operating on planetary surfaces, in atmospheric systems, and possibly in subsurface oceans on moons orbiting gas giant planets. By 9 to 10 billion years after the Big Bang, the universe has developed most of the structural complexity we observe today. Galaxy morphologies are well established, the cluster hierarchy is mature, and the cosmic web provides a stable framework for continued evolution. Star formation continues, but at steadily declining rates as the available gas supplies are gradually consumed or heated to temperatures that prevent further cooling and collapse. The stage is set for the next great chapter in cosmic evolution, the era when dark energy begins to dominate the universe's expansion, accelerating the growth of space itself and ushering in the long, slow decline toward the far future when star formation will cease entirely and the universe will enter its final cold phase. Chapter 11. Our solar system forms, a cosmic oasis. Time: 9 billion years after the Big Bang, 4.6 billion years ago, in a quiet spiral arm of a mature galaxy we now call the Milky Way, something remarkable is about to happen. A slowly rotating cloud of gas and dust, enriched by billions of years of stellar evolution, begins to collapse under its own gravity. This is the birth of our solar system, the cosmic neighborhood that will eventually nurture the only known life in the universe. The universe is now 9.2 billion years old, well into its mature phase. Star formation has declined significantly from the peaks of cosmic high noon, but it continues at a steady pace throughout spiral galaxies like our own. The interstellar medium has been enriched by countless generations of stars to the point where roughly 2% of its mass consists of elements heavier than hydrogen and helium, carbon, oxygen, silicon, iron, and dozens of other elements essential for rocky planet formation. Our story now becomes deeply personal, for we're witnessing the formation of the system that will one day give rise to Earth and, eventually, to conscious beings capable of contemplating their own cosmic origins. As you listen to this tale of our cosmic birthplace, what time marks your journey through this evening? Are you settling into the peaceful hours as we explore how peace itself, in the form of a stable planetary system, first became possible? The solar nebula, as astronomers call this primordial cloud, spans several light years and contains enough material to form hundreds of systems like ours. But most of this material will be dispersed by stellar winds from nearby massive stars. Only a tiny fraction, about 1% of the original cloud, will actually condense to form the sun and planets. The collapse begins slowly, possibly triggered by the shock wave from a nearby supernova explosion. As the cloud contracts, it begins to spin faster, flattening into a disk with a dense concentration at the center. Within a few 100,000 years, the central condensation becomes hot and dense enough to begin nuclear fusion. Our sun ignites, beginning its 10 billion-year journey as a main sequence star. The young sun is quite different from the stable star we know today. It's about 30% dimmer, but also much more active, producing frequent flares and intense stellar winds that sweep through the solar system. These early solar winds help clear away much of the remaining gas from the solar nebula, leaving behind a disk of dust and rocky particles that will eventually coalesce into planets. The process of planetary formation is both elegant and violent. Tiny dust grains stick together through electrostatic forces, forming pebbles. Pebbles collide and merge to create boulders. Boulders accumulate into asteroids, and asteroids, through countless collisions over millions of years, gradually build up into the rocky cores of terrestrial planets. In the inner solar system, where temperatures are high enough to vaporize volatile compounds like water and methane, only rocky and metallic materials can condense. This is where Mercury, Venus, Earth, and Mars will form small, dense worlds composed primarily of silicon, iron, and other refractory elements forged in the nuclear furnaces of ancient stars. Further from the sun, beyond what astronomers call the frost line, temperatures are low enough for water ice to condense. Here, planetary formation proceeds much more rapidly because ice is abundant, allowing planetary cores to grow large enough to gravitationally capture the hydrogen and helium gas still present in the outer nebula. This is how Jupiter and Saturn form, massive gas giants with small rocky cores surrounded by thick atmospheres of primordial gas. The formation of Jupiter has profound effects throughout the solar system. Its immense gravity acts like a cosmic vacuum cleaner, capturing or ejecting many of the asteroids and comets that might otherwise bombard the inner planets. But Jupiter's influence is more subtle as well. Its gravitational pull affects the orbits of forming planets throughout the system, ultimately determining the final architecture of planetary orbits. What's your local time as we witness the birth of our cosmic home? Whether it's evening or the deeper quiet of night, we're exploring the formation of the only place in the universe we know with certainty harbors life. The early solar system is a chaotic place. Planetary formation involves countless collisions, some so violent they can completely reshape or even destroy the worlds involved. Earth itself likely suffered a collision with a Mars-sized object called Theia, an impact so tremendous that it vaporized much of both worlds and ejected enough material into orbit to form the Moon. This collision, catastrophic as it was, may have been essential for life's eventual emergence on Earth. The impact stripped away most of Earth's original atmosphere, allowing a new one to form from volcanic outgassing. It also gave Earth its unusually large moon, which stabilizes our planet's axial tilt and creates tides that may have been crucial for early biochemical evolution. As the solar system matures over its first few 100 million years, the bombardment of asteroids and comets gradually subsides. The planets settle into stable orbits, their surfaces cool and solidify, and the stage is set for the next great chapter in our cosmic story, the emergence of life itself. Earth at this time is a water world with a thin atmosphere of carbon dioxide, nitrogen, and water vapor. Volcanic activity is intense, continuously reshaping the surface and releasing gases that will eventually form our breathable atmosphere. Lightning crackles through dense clouds, and the young sun's variable output creates a constantly changing climate. Yet within this apparently hostile environment, the first stirrings of life may already be beginning. Simple organic molecules form in the primitive oceans, possibly aided by the energy from lightning, volcanic activity, or ultraviolet radiation from the young sun. The chemical ingredients for life, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, are all present, dissolved in liquid water under conditions that allow complex chemistry to proceed. By 4 billion years ago, just 600 million years after the solar system's formation, the first simple cells appear in Earth's oceans. These earliest organisms are prokaryotes, bacteria and archaea without complex internal structures. But they represent one of the most important transitions in cosmic history, the emergence of life from purely chemical processes. Our solar system's formation represents a crucial milestone in the universe's evolution toward complexity. For the first time in cosmic history, we have a stable environment where liquid water can persist for billions of years, where heavy elements are abundant enough to support complex chemistry, and where conditions are just right for the slow development of increasingly sophisticated biological systems. As we leave this chapter of solar system formation, Earth is poised to become the stage for an even more remarkable story, the evolution of simple cells into the incredible diversity of life we see today, ultimately leading to the emergence of intelligence and consciousness capable of understanding the cosmic story of which it is a part. Chapter 12. Life Awakens, the Biological Revolution. Time, 4 billion years ago to 500 million years ago. On a small blue world orbiting an ordinary star in an unremarkable spiral galaxy, something unprecedented happens. For the first time in the universe's 9.8 billion year history, matter organizes itself into patterns capable of reproduction, growth, and evolution. Life emerges from the chemistry of early Earth, beginning a biological revolution that will ultimately lead to consciousness and intelligence. The early Earth where life first appears is almost unrecognizable compared to our modern world. The atmosphere contains virtually no oxygen. It's composed mainly of nitrogen, carbon dioxide, methane, and water vapor. The surface is frequently reshaped by volcanic activity, meteor impacts, and the gradual cooling of the planet from its violent formation period. Yet within this harsh environment, the basic chemistry of life finds a way to emerge. In tidal pools, deep ocean vents, or perhaps in microscopic mineral chambers, simple organic molecules begin to organize into increasingly complex structures. Amino acids link together to form primitive proteins. Nucleotides assemble into the first genetic molecules. And somehow, through processes we're still trying to understand, these chemicals cross the threshold from complex chemistry to simple life. As you drift through this tale of life's emergence, what quiet hour marks your own evening? Are you finding peace in the darkness as we explore how the universe first awakened to itself through the emergence of living systems? The first organisms are prokaryotes, simple cells without internal compartments or complex structures. They're microscopic, but they represent one of the most important innovations in cosmic history. The ability to capture energy from their environment, grow, reproduce, and pass information to their offspring through genetic material. These early life forms are remarkably sophisticated despite their apparent simplicity. They develop biochemical pathways to extract energy from their environment, some through fermentation of organic molecules, others through primitive forms of photosynthesis that don't yet produce oxygen. They evolve mechanisms to repair damage, to reproduce with remarkable fidelity, and to respond to environmental changes. For nearly 2 billion years, these prokaryotic cells dominate Earth's biosphere. During this vast period, longer than the time from prokaryotes to humans, life remains microscopic and largely invisible. Yet fundamental innovations continue to accumulate. Different species of bacteria and archaea explore every possible ecological niche, from boiling hot springs to frozen polar regions, from the deepest ocean trenches to the upper atmosphere. Around 2.5 billion years ago, one group of prokaryotes develops a new form of photosynthesis that uses water as an electron donor, releasing oxygen as a waste product. This innovation by cyanobacteria triggers one of the most dramatic environmental changes in Earth's history, the Great Oxidation Event. Oxygen is initially toxic to most life forms, which evolved in an oxygen-free environment. The accumulation of oxygen in the atmosphere causes a mass extinction, eliminating many of the original prokaryotic species. But oxygen also opens up new possibilities for life. It enables more efficient forms of cellular respiration that can extract far more energy from organic molecules than anaerobic processes. The oxidation of Earth's atmosphere also has cosmic consequences. Oxygen reacts with methane in the atmosphere, reducing the greenhouse effect and triggering a series of global ice ages. For hundreds of millions of years, Earth becomes a snowball, frozen from pole to pole with ice sheets extending into the tropics. Yet life persists, adapting to these extreme conditions and continuing to evolve. What time is it in your peaceful world as we explore life's persistence through cosmic challenges? Whether it's evening or night where you are, we're witnessing how life itself became a cosmic force, capable of transforming entire planetary atmospheres. Around 1.8 billion years ago, another crucial innovation appears: the eukaryotic cell. These are much larger and more complex than prokaryotes, with internal compartments called organelles that allow for specialized functions. The mitochondria that power our cells today are actually ancient bacteria that entered into symbiotic relationships with early eukaryotes, creating a new form of cellular organization. Eukaryotic cells remain single-celled for another billion years, but they develop increasingly sophisticated behaviors. Some become mobile, using flagella or other structures to swim through their environment. Others develop the ability to engulf and digest other cells, becoming the first predators. Still others form temporary colonies that can coordinate their behavior in simple ways. The first multicellular organisms appear around 1 billion years ago, simple clusters of cells that remain connected after division and begin to specialize for different functions. This represents another fundamental threshold in the organization of matter. For the first time, individual cells sacrifice their independence to become part of larger, more complex structures. Multicellularity opens up entirely new possibilities for life. Organisms can grow larger, develop specialized tissues, and exploit resources that single cells cannot access. They can develop complex behaviors, respond to environmental changes more effectively, and explore new ecological niches. By 600 million years ago, the first complex multicellular organisms appear in the fossil record. The Ediacaran fauna includes some of the strangest creatures ever to inhabit Earth, soft-bodied organisms with symmetries and body plans unlike anything alive today. Many resemble quilted discs, fronds, or tubes, and their relationship to modern life forms remains mysterious. The stage is set for one of the most dramatic episodes in the history of life on Earth, the Cambrian explosion, beginning around 540 million years ago. In a relatively brief period of geological time, most of the major groups of animals appear in the fossil record, displaying a diversity of body plans, behaviors, and ecological strategies that establish the basic framework for all future animal evolution. The Cambrian seas teem with bizarre and wonderful creatures. Trilobites scuttle across the seafloor with their compound eyes, some of the first sophisticated visual systems in Earth's history. Anomalocaris, a meter-long predator with grasping arms and circular jaws, patrols the water column. Hallucigenia walks on stilted legs with spines projecting from its back, while Opabinia sweeps the seafloor with its vacuum cleaner proboscis. This explosion of biological diversity represents life's first great experiment with complex multicellular forms. In just a few tens of millions of years, evolution explores most of the basic body plans that will constrain animal life for the next half-billion years. The fundamental toolkit of animal development, genes that control body axis formation, tissue specification, and organ development crystallizes during this period. By 500 million years ago, life has established itself as a major geological force on Earth. Organisms build reefs, alter atmospheric composition, and begin the slow process of colonizing the land. The biological revolution that began with simple cells in ancient oceans has set the stage for the next great chapter in Earth's story, the conquest of land and the eventual emergence of intelligence. Chapter 13. The acceleration begins, dark energy awakens. Time 5 billion years ago to present. As life on Earth undergoes its remarkable evolutionary journey, the universe itself enters a new phase of its existence. Around 5 billion years ago, coincidentally, about the same time our solar system was forming, a mysterious force begins to dominate cosmic evolution. Dark energy, comprising roughly 68% of the universe's total energy budget, starts to accelerate the expansion of space itself. This marks one of the most profound transitions in cosmic history. For nearly 9 billion years, the universe's expansion had been steadily slowing under the gravitational influence of matter and dark matter. Galaxies, while still moving apart due to cosmic expansion, were doing so at an ever-decreasing rate. Many cosmologists expected this deceleration to continue indefinitely, perhaps even reversing into a cosmic collapse, the Big Crunch. Instead, observations of distant supernovae in the 1990s revealed something completely unexpected. The universe's expansion is accelerating. Space itself is growing faster and faster, driven by a form of energy that permeates every cubic centimeter of the cosmos yet remains almost completely mysterious to us. As you continue this cosmic journey, what time marks your own quiet evening? Are you settling deeper into rest as we explore how the universe itself began a restless acceleration that continues to this day? The nature of dark energy remains one of the greatest puzzles in modern physics. It behaves unlike any form of matter or energy we understand. While ordinary matter becomes more dilute as the universe expands, dark energy maintains constant density. As space grows, more dark energy appears to fill it, creating a repulsive force that pushes against gravity and accelerates cosmic expansion. Einstein's equations actually predicted the possibility of such a force. He called it the cosmological constant, but he considered it his greatest blunder when observations seemed to show a static universe. Now we know that Einstein's cosmological constant, or something very much like it, may be the most important component of our cosmos. The effects of dark energy are subtle at first. Within galaxy clusters and individual galaxies, gravity remains dominant, holding these structures together against the accelerating expansion. But on larger scales, between galaxy clusters and superclusters, dark energy begins to win the cosmic tug-of-war with gravity. This has profound implications for the future of cosmic structure formation. The era of building larger and larger structures through gravitational collapse is coming to an end. Existing galaxy clusters will continue to evolve internally, but new clusters become increasingly unlikely to form as dark energy pulls their potential member galaxies apart faster than gravity can bring them together. The cosmic web structure that took billions of years to develop will gradually dissolve. The vast filaments of dark matter that connect galaxy clusters will stretch and thin as dark energy drives accelerating expansion. Eventually, these connections will break entirely, leaving galaxy clusters as isolated islands in an increasingly empty universe. Within our local group of galaxies, which includes the Milky Way, Andromeda, and several dozen smaller galaxies, gravity still dominates over dark energy. This small collection of galaxies will continue to evolve under gravitational influence, with the Milky Way and Andromeda destined to merge in about 4 billion years to form a single, large elliptical galaxy that astronomers whimsically call Milkomeda. What's your local time as we contemplate this cosmic acceleration? Whether it's evening or the deeper quiet of night, we're exploring how the universe began its journey toward an increasingly empty and isolated future. The accelerating expansion affects our cosmic horizon as well. There's a limit to how far we can see in the universe, not just because light takes time to travel, but because space itself is expanding. Light from very distant galaxies becomes increasingly redshifted and dimmed by cosmic expansion. As acceleration continues, this cosmic horizon will gradually shrink, making distant galaxies disappear from view forever. Future civilizations, if they arise billions of years from now, will inhabit a very different cosmic environment. They'll see only the galaxies in their local gravitational neighborhood, perhaps just their own galaxy cluster or group. The cosmic microwave background radiation will have been redshifted to such long wavelengths that it becomes undetectable. The evidence for the Big Bang, dark matter, and dark energy that we take for granted today will have faded beyond recognition. This cosmic acceleration also affects the long-term fate of the universe. Instead of eventually recollapsing in a big crunch, the universe will continue expanding forever, growing ever colder and more dilute. We're entering what cosmologists call the stelliferous era, the age when stars shine and provide energy for complex processes. But this era has a definite end point. As dark energy continues to dominate, the universe will eventually reach a state where no new structures can form, no new stars can ignite, and the existing stellar populations slowly age and die. We're witnessing the beginning of the universe's long, slow decline toward maximum entropy, the heat death that represents the ultimate fate of our cosmos. Yet this distant future is still trillions of years away. For now, we live in a remarkably favorable epoch. Stars continue to shine, planets continue to orbit in stable systems, and life continues to evolve and explore the cosmos. The acceleration driven by dark energy is gentle enough that it doesn't disrupt local structures, but strong enough to guarantee that the universe will remain dynamic and continue evolving for an almost incomprehensible length of time. As we move from this era of acceleration toward the present day, we're approaching the moment when intelligence emerges on Earth and begins to contemplate its cosmic origins. The universe, now 13.8 billion years old, has produced at least one world where matter has organized itself into forms complex enough to understand the very cosmic story of which it is a part. Chapter 14, Intelligence Emerges. The universe becomes self-aware. Time 3.8 billion years ago to present. On the third planet orbiting a yellow dwarf star in the outer spiral arm of an ordinary galaxy, something extraordinary happens. After 3.8 billion years of biological evolution, life develops the capacity for abstract thought, language, and scientific understanding. For the first time in cosmic history, the universe becomes capable of understanding itself through the emergence of intelligence. This transformation doesn't happen overnight. The journey from simple prokaryotic cells to conscious, thinking beings unfolds over billions of years through countless innovations and evolutionary experiments. Each step builds upon the previous ones, creating layers of complexity that eventually give rise to minds capable of contemplating their own existence and place in the cosmos. The story of life's colonization of land begins around 500 million years ago. Plants developed the ability to photosynthesize using sunlight, carbon dioxide, and water, gradually increasing atmospheric oxygen levels and creating the foundation for more complex ecosystems. Animals follow, adapting to terrestrial environments and diversifying into the incredible variety of forms we see in the fossil record. Through the Paleozoic era, life experiments with increasingly sophisticated body plans and behaviors. Fish develop jaws and eventually limbs, becoming the first vertebrates to venture onto land. Forests of primitive trees transform the landscape, creating new ecological niches and fundamentally altering Earth's climate and atmospheric composition. As you drift through this tale of life's expanding complexity, what quiet moment marks your evening? Are you finding peace in these late hours as we explore how the universe developed the capacity to find peace and meaning in its own existence? The great mass extinctions that punctuate Earth's history, including the devastating Permian extinction 252 million years ago that eliminated 96% of marine species, actually accelerate evolution by clearing ecological space for new innovations. Each recovery period sees life explore new possibilities, develop new strategies, and achieve new levels of complexity. The rise of dinosaurs during the Mesozoic era represents one of evolution's most successful experiments with large-scale multicellular organization. For over 160 million years, these remarkable creatures dominate terrestrial ecosystems, evolving into forms ranging from massive long-necked sauropods to intelligent pack-hunting theropods. Some dinosaurs developed sophisticated social behaviors, complex nesting strategies, and possibly even proto-cultural transmission of information. The asteroid impact 66 million years ago that ends the age of dinosaurs creates opportunities for mammals, small, warm-blooded creatures that had lived in the shadows of their reptilian contemporaries. The Cenozoic era witnesses explosive mammalian diversification, with species adapting to every available ecological niche from the deep ocean to the forest canopy. Among these diversifying mammals, one lineage proves particularly significant for cosmic history. The primates, initially small, tree-dwelling creatures with forward-facing eyes and grasping hands, begin developing increasingly sophisticated behaviors. Social cooperation, tool use, and complex communication gradually emerge within primate societies. The African apes represent a crucial branch in this evolutionary tree. Around 7 to 8 million years ago, climate changes in Africa create new selective pressures that favor upright locomotion, larger brains, and more sophisticated tool use. The hominin lineage begins its remarkable journey toward modern human intelligence. What time is it in your world as we approach the emergence of consciousness itself? Whether it's evening or night where you are, we're exploring the universe's most remarkable achievement, the development of minds capable of understanding their cosmic context. The evolution of human intelligence accelerates dramatically over the past few million years. Brain size increases threefold from early Australopithecines to modern humans. Language develops, allowing the transmission of complex ideas across generations. Cultural evolution begins to supplement biological evolution, with knowledge and innovations accumulating far faster than genetic changes. Homo sapiens emerges around 300,000 years ago, but the full flowering of human cognitive abilities appears more recently. The development of symbolic thought, art, music, and sophisticated tool technologies around 50,000 to 100,000 years ago marks the beginning of truly modern human behavior. For the first time, matter has organized itself into patterns capable of creating meaning, beauty, and understanding. The agricultural revolution 10,000 years ago allows human populations to grow and develop complex societies. Writing systems preserve knowledge across generations, while mathematics and early scientific observations begin the systematic study of natural phenomena. Humans begin to recognize patterns in the motions of celestial objects, laying the groundwork for astronomy, the science that will eventually reveal our cosmic origins. The scientific revolution of the past 500 years represents an exponential acceleration in humanity's understanding of the universe. Galileo's telescope reveals that we're not at the center of the cosmos. Newton's laws of motion and gravitation show that the same physical principles operate throughout the universe. Darwin's theory of evolution demonstrates that all life shares common ancestry and that complexity can emerge through natural processes. The 20th century brings even more dramatic revelations. Einstein's relativity theories show that space and time are dynamic and interconnected. Hubble's observations reveal that the universe is expanding and much larger than anyone imagined. The discovery of the cosmic microwave background provides direct evidence for the Big Bang, while quantum mechanics reveals the strange and wonderful nature of reality at the smallest scales. Modern astronomy and cosmology have given us an increasingly complete picture of our cosmic story. We now know that we're made of elements forged in the nuclear furnaces of ancient stars, that our galaxy is one of hundreds of billions in the observable universe, and that the cosmos has been evolving for 13.8 billion years through processes we can study and understand. Perhaps most remarkably, we've learned that the emergence of intelligence appears to be a natural consequence of cosmic evolution. The same physical laws that govern stellar nucleosynthesis and galaxy formation also govern the chemistry of life and the development of complex nervous systems. Consciousness isn't separate from the physical universe. It's one of the most sophisticated expressions of the universe's inherent tendency toward increasing complexity. Today, human intelligence continues to explore and understand the cosmos through increasingly powerful tools. Space telescopes peer back toward the cosmic dark ages, searching for the first stars and galaxies. Particle accelerators recreate conditions that existed in the first moments after the Big Bang. Computer simulations model the evolution of cosmic structure over billions of years. We've also begun to search for other intelligences in the universe. The Drake equation suggests that technological civilizations might be common, while the Fermi paradox questions why we haven't encountered them yet. Recent discoveries of thousands of exoplanets, including many in the habitable zones of their stars, suggest that Earth-like worlds may be abundant throughout the galaxy. As we stand at this moment in cosmic history, 13.8 billion years after the Big Bang, we represent the universe's current frontier of self-awareness. Through human minds and the scientific instruments we've created, the cosmos contemplates its own existence, marvels at its own beauty, and seeks to understand its own ultimate fate. We are the universe becoming conscious of itself, matter organizing into patterns capable of wonder, curiosity, and understanding. In us, the cosmos has developed eyes to see its own vastness, minds to comprehend its own evolution, and hearts to be moved by its own magnificent story. Chapter 15. The Deep Future Toward the Final Darkness. Time, present to 10 to the power of 100 years and beyond. As we rest in the present moment, you in your peaceful evening, and the universe at 13.8 billion years of age, we stand at a remarkable vantage point in cosmic history. Behind us stretches the epic story of creation, from the Big Bang through the formation of stars, galaxies, and life itself. Ahead lies an almost incomprehensibly vast future, stretching not just billions or trillions of years, but to timescales that dwarf the current age of the universe. The future cosmos will be shaped primarily by two forces: the continued acceleration driven by dark energy and the relentless increase in entropy described by the second law of thermodynamics. Together, these forces will guide the universe through a series of dramatic transformations, each more profound than the last. Our journey into the deep future begins with changes we can observe already beginning. The Milky Way and Andromeda galaxies are approaching each other at 250,000 miles per hour, destined to merge in approximately 4.5 billion years. This galactic collision will be spectacular but not catastrophic. Stars are so widely spaced that direct collisions will be rare. Instead, gravitational interactions will fling some stars into intergalactic space, while others spiral toward the merged galaxy's center. As you drift through this vision of the far future, what time accompanies your journey tonight? Are you in the quiet depths of evening as we explore how the universe itself approaches its own form of eternal rest? The merger of our galaxy with Andromeda will create a giant elliptical galaxy, Milkomeda, that will dominate our local group. By this time, dark energy will have pushed most other galaxy groups and clusters beyond our cosmic horizon. Future inhabitants of Milkomeda will see a much lonelier universe, with only a few dozen nearby galaxies visible in their night sky. Over the next 100 billion years, star formation throughout the universe will gradually cease. The supply of hydrogen gas, the raw material for new stars, will be exhausted as existing gas either forms stars or is heated by stellar winds and supernova explosions to temperatures too high for gravitational collapse. The era of stellar birth, which has lasted for over 13 billion years, will come to an end. This transition marks the beginning of what cosmologists call the degenerate era. The universe will be populated primarily by stellar remnants, white dwarf stars, the cooling cores of sun-like stars, neutron stars, the ultradense remains of massive stars, and black holes, formed from the most massive stars and galactic centers. These objects will shine weakly as they slowly radiate away their stored thermal energy. Brown dwarfs, failed stars that never achieved nuclear fusion, will become increasingly important during this era. As they cool and contract under gravity, some may eventually reach the temperatures and densities needed for nuclear fusion, becoming the last conventional stars to shine in the cosmos. These dim red dwarfs could continue burning for trillions of years, providing the final sources of stellar energy in an increasingly cold universe. The longest-lived stars currently shining red dwarf stars with masses less than half our Sun will continue burning for 1 to 10 trillion years. Long after our Sun has swollen into a red giant and collapsed into a white dwarf, these dim stellar embers will continue their slow consumption of hydrogen fuel. They represent the universe's last gasp of conventional stellar activity. What time marks your peaceful evening as we contemplate these vast timescales? Whether it's night or the quiet hours before dawn, we're exploring epochs so distant that the entire history of the universe to this point becomes just the opening chapter of an incomparably longer story. As stellar evolution continues over these enormous timescales, white dwarf stars will slowly cool and crystallize, becoming cold, dark objects known as black dwarfs. Neutron stars will also cool, though their dense matter may undergo exotic phase transitions as temperatures drop toward absolute zero. The universe will become increasingly dark and cold. But even in this seemingly dead cosmos, remarkable events will continue to occur, albeit at incredibly slow rates. Quantum mechanics predicts that protons, the building blocks of atomic nuclei, are not perfectly stable. With a half-life estimated at 10 to the power of 34 years, protons will eventually decay into lighter particles and energy. This process will cause even the most stable matter to gradually disintegrate. The decay of protons marks the beginning of the black hole era, when these exotic objects become the dominant form of matter in the universe. As conventional matter dissolves, black holes will grow through the accretion of the resulting particles and radiation. Galaxy-mass black holes will gradually consume the stellar remnants in their vicinity, growing to enormous sizes. But black holes are not eternal either. Stephen Hawking's groundbreaking work showed that all black holes emit radiation and gradually evaporate. The rate of this Hawking radiation is inversely proportional to the black hole's mass. Smaller black holes evaporate faster than larger ones. A black hole with the mass of our Sun would take 10 to the power of 67 years to completely evaporate, while supermassive black holes containing billions of solar masses will persist for 10 to the power of 100 years or more. During the black hole era, these slowly evaporating objects will be the primary source of energy in the universe. Their Hawking radiation will provide the only significant source of heat and light in an otherwise completely dark cosmos. As bizarre as it sounds, black holes may represent the final refuges where complex processes, and possibly even life, could persist in the far future. The evaporation of the last black holes marks the beginning of the dark era, a time when the universe contains only elementary particles, photons, and perhaps exotic particles we haven't discovered yet. The temperature will approach absolute zero, and the density will become unimaginably low as space continues to expand under the influence of dark energy. In this final era, quantum mechanical effects may become important on cosmic scales. Some theories predict that quantum tunneling could cause the universe to spontaneously transition to a lower energy state. A vacuum decay that would destroy everything we know and possibly create entirely new forms of physics. Other theories suggest that quantum fluctuations might occasionally create small regions of higher density that could evolve into new universes. The timescales involved in these final cosmic epochs are so vast they challenge human comprehension. The age of the universe when the last stars fade, about 100 trillion years, is roughly 7,000 times longer than the current age of the cosmos. The time when the last black holes evaporate is incomparably longer still. If the current age of the universe were compressed into a single second, the black hole era would last longer than the current age of the universe raised to the power of itself. Yet even facing this ultimate fate, there's something profoundly beautiful about the cosmic story. The universe that began as a quantum fluctuation 13.8 billion years ago has succeeded in organizing matter into forms complex enough to understand and appreciate its own existence. In the brief cosmic moment when stars shine and planets orbit in stable systems, the universe has achieved consciousness, created beauty, and found meaning. Perhaps most remarkably, the very fact that we can contemplate these vast futures represents a triumph of cosmic evolution. We are the universe's way of knowing itself, of marveling at its own vastness, and of finding profound meaning in its epic story of transformation from simplicity to complexity and back to simplicity again. Chapter 16. The Eternal Return Beyond Time Itself. Time, beyond 10 to the power of 100 years, the ultimate future. As our cosmic journey approaches its conclusion, we venture into realms so distant in time that the concepts of past, present, and future begin to lose their conventional meaning. We're exploring epochs when the universe will have expanded to such enormous size and cooled to such low temperatures that the very nature of existence itself may be transformed. In the darkest depths of the far future, when the last black holes have evaporated and the universe contains only a sparse gas of elementary particles and photons, something remarkable may still occur. The universe will continue expanding under the influence of dark energy, but quantum mechanics suggests that even in this apparently empty cosmos, spontaneous fluctuations can still create organized structures. The timescales involved are beyond human comprehension. We must think in terms of 10 carat 10 carat 76 years, a number so large that if every digit were written in a font so small that a billion digits could fit in the period at the end of this sentence, the number would still be larger than the observable universe. Yet given infinite time, quantum mechanics predicts that random fluctuations will eventually recreate any possible arrangement of matter, including exact duplicates of everything that has ever existed. As you continue this journey through the deepest cosmic night, what time marks your own approach to rest? Are you in those peaceful hours when sleep beckons, making this the perfect moment to contemplate the universe's own approach to its ultimate slumber? In this unimaginably distant future, quantum fluctuations might spontaneously create not just individual particles, but entire organized structures. A random fluctuation could produce a brain identical to yours, complete with all your memories and thoughts, existing for a brief moment before dissolving back into the quantum foam. Such Boltzmann brains would be vastly more common than brains that evolved through biological processes, since evolution requires special initial conditions while quantum fluctuations are truly random. Even more remarkably, these same quantum processes could recreate entire worlds, solar systems, or even observable universes identical to ours. Given sufficient time, and we have infinite time available, every possible arrangement of matter that's consistent with the laws of physics will eventually appear through random quantum fluctuations. This includes perfect recreations of Earth, complete with its entire history and every person who has ever lived. The philosophical implications are staggering. If these quantum fluctuations can recreate any possible state of matter, then in some sense nothing is ever truly lost. Every moment of beauty, every act of love, every scientific discovery, and every work of art will eventually be recreated through the random motion of particles in the far future cosmos. Some cosmological theories suggest even more exotic possibilities for the ultimate future. If dark energy is not truly constant but instead changes over time, the expansion of the universe might eventually reverse, leading to a big crunch that compresses all matter and energy back into a hot, dense state similar to the Big Bang. This could trigger a new cycle of cosmic evolution, a new universe with new stars, galaxies, and possibly new forms of life and intelligence. Other theories propose that our universe might be just one of countless bubble universes in an eternal inflation scenario. In this view, new universes are constantly being created through quantum fluctuations in a higher dimensional space, each with its own physical laws and constants. Our observable universe would be just one temporary bubble in an infinite cosmic ocean. What's your local time as we explore these ultimate mysteries? Whether it's night or the quiet hours before dawn, we're contemplating possibilities so profound they transform our understanding of existence itself. The concept of eternal inflation raises the possibility that every possible universe, every possible set of physical laws, every possible arrangement of matter and energy already exists somewhere in this infinite multiverse. In such a scenario, our cosmic story isn't unique, but rather one of infinitely many variations on the theme of existence. Yet another possibility emerges from our growing understanding of quantum gravity and the nature of space-time itself. Some theories suggest that time may not be fundamental, but rather an emergent property of more basic processes. In the deepest level of reality, past, present, and future might all exist simultaneously in a timeless quantum state where all possibilities coexist. If time is indeed emergent rather than fundamental, then the cosmic story we've traced, from the Big Bang through stellar evolution to the far future, might be better understood as a pattern in a timeless quantum reality rather than a sequence of events unfolding in time. From this perspective, every moment in cosmic history exists eternally, and our journey through time is simply our consciousness moving through different aspects of this eternal pattern. These ultimate questions touch on the deepest mysteries of existence. Why is there something rather than nothing? What is the nature of consciousness and its relationship to the physical universe? Are the laws of physics themselves eternal, or do they emerge from even more fundamental principles? As we approach the end of our cosmic journey, we find ourselves confronting the same sense of wonder and mystery that motivated the first humans to look up at the night sky and ask profound questions about their place in the universe. Despite all our scientific advances, the ultimate nature of reality remains as mysterious and beautiful as ever. Perhaps this is as it should be. The universe has succeeded in creating beings capable of contemplating infinity, of finding meaning in vast cosmic cycles, and of experiencing awe at the sheer improbability and beauty of existence itself. We are patterns of matter and energy that have become conscious of our own cosmic origins and ultimate fate. In us, the universe has achieved something remarkable. The ability to look back on its own 13.8 billion-year history with wonder, to find beauty in its own structures and processes, and to contemplate its own infinite future with a mixture of humility and awe. We are the cosmos becoming conscious of itself, temporary arrangements of atoms that can nevertheless grasp eternal truths about the nature of existence. As our journey through cosmic time draws to a close, we return to the present moment. To you, listening to this tale in your own peaceful evening, and to the remarkable fact that the universe has organized itself into forms complex enough to understand and appreciate its own magnificent story. In the end, perhaps the most profound truth revealed by our cosmic journey is this: we are not separate from the universe, observing it from the outside. We are the universe itself, evolved to the point of self-awareness. In our consciousness, the cosmos knows itself. In our wonder, it experiences awe at its own beauty. And in our scientific understanding, it comprehends its own deepest truths. Closing, the eternal now. And so, fellow cosmic wanderer, we complete our journey through the greatest story ever told, the biography of the universe itself, from its first moment of existence to its ultimate fate in the unimaginably distant future. We began with nothing, no space, no time, no matter, no energy, and witnessed the spontaneous emergence of everything from quantum fluctuations in a primordial vacuum. We watched as fundamental forces separated, as the first particles formed, and as nuclear processes forged the first atomic nuclei in the cosmic furnace of Big Bang nucleosynthesis. We observed the universe's first dawn as electrons joined with nuclei to form neutral atoms, releasing the cosmic microwave background radiation that we can still detect today. Through the dark ages, we witnessed the patient construction of cosmic structure under gravity's influence, building the scaffolding upon which all future complexity would rest. We celebrated the ignition of the first stars, massive, brilliant beacons that ended the cosmic darkness and began the universe's chemical evolution by forging heavy elements in their nuclear cores. We watched as these stellar pioneers died in spectacular explosions, scattering the seeds of future planets and life throughout the cosmos. We traced the formation of galaxies, the birth of quasars, and the universe's peak period of star formation when the cosmos blazed with the fury of stellar birth. We witnessed the gradual maturation of cosmic structure and the emergence of the large-scale cosmic web that defines the universe's architecture today. In our own cosmic neighborhood, we explored the formation of the solar system from a slowly rotating cloud of gas and dust enriched by billions of years of stellar evolution. We marveled at the emergence of life on Earth, its evolution through countless innovations, and its eventual development of intelligence capable of understanding its own cosmic origins. We contemplated the universe's acceleration under the influence of dark energy, its ultimate expansion into cold emptiness, and the exotic possibilities that might emerge in the vast expanses of deep time when quantum fluctuations become the dominant creative force in existence. Throughout this cosmic epic, we've seen the universe's remarkable capacity for self-organization, its tendency to build complexity from simplicity, and its ability to create structures of stunning beauty and sophistication. From the elegant spiral arms of galaxies to the intricate chemistry of living cells, the cosmos demonstrates an inherent creativity that produces wonder at every scale. Most remarkably, we've seen how this cosmic creativity has culminated in the emergence of consciousness itself. In minds capable of contemplating infinity, hearts capable of being moved by beauty, and intelligences capable of understanding their own place in the vast cosmic story. As you rest in your peaceful evening, wherever you are in the world, whatever time marks your journey through this tale, remember that you are not separate from this cosmic story. You are its latest chapter, its current frontier of self-awareness, its way of knowing and appreciating itself. The iron in your blood was forged in the nuclear furnace of a dying star. The calcium in your bones was created in the explosive death throes of a stellar giant. The oxygen you breathe was manufactured in stellar cores and scattered through space by ancient supernovae. You are, quite literally, made of star stuff, the universe's way of organizing matter into patterns complex enough to understand its own existence. In this moment, as you listen to these words, you represent 13.8 billion years of cosmic evolution. You are the universe's memory of its own past, its awareness of its own present, and its contemplation of its own future. Through your consciousness, the cosmos experiences wonder at its own vastness, beauty at its own structures, and meaning in its own magnificent story. Rest well, cosmic traveler, knowing that you carry within yourself the entire history of the universe, from the first moment of creation to this present instant of awareness. In you, the cosmos sleeps and dreams of its own infinite possibilities. Sweet dreams, fellow child of the stars. The universe dreams with you,